Good morning, everyone. So we are into chapter 6, okay, and which is about scalar field problems. We have already derived the 2D heat conduction problem, and yesterday we were trying to find out solution of Laplace equation, which is the simplest form of the 2D heat transfer problem, heat conduction problem. Okay, and what you typically use is called a separation of variables, which you write as txy is as a product of two functions, one a pure function of x, the other pure function of y, basically. Yeah, so accordingly we put the we analyzed it, and finally we found out that this first we assumed alpha, this one has to be positive, and then we found out the solution, and then we realized that when you have alpha greater than 0, then the boundary condition cannot be satisfied. So in that case, what happens? We have to take alpha as negative, and hence we used alpha is negative minus beta square, where beta is unknown. Okay, so remember this is beta is unknown. We also have to find out beta itself. Yeah. So anyway, we did this analysis, and then we found out two kinds of solutions. One for coming from x, yeah, and which is based on the two boundary conditions. We found that this x is a sinusoidal function, right? So x, what we get is, so x is equal to this, yeah. Sorry. This is what you get is x this, and out of which C9 you have C9 multiplied by this equal to 0. So from there, if this is equal to 0, then beta has to be n pi, yeah, and hence you write this as 0 to n summation. You can actually, this is the general solution you can get for that, yeah. However, remember that this value, whatever we get from here, yeah, so this we need to remember, which applies to basically for the other equation as well, because we get the beta value from here. So we have to write beta equal to n pi over a, right, where n is given like this one. Same beta we have to use in the second equation. Yeah, so second equation is here like this one. This we did the analysis here. The first boundary condition tx0 has to be equal to 0, so that makes it as the coefficient of cos is equal to 0, and the other boundary condition, y is given by this one. Okay. Now we try to find out, because at this point at y equal to b, the value is x square, t is equal to x square. So we attempted to find out the coefficient by that. So the t values, so basically what you get here is this one. So t xb is equal to xx, so yb has to be equal to x squared, so this is equal to a square, right? Then so everything we did fine, yeah. So just a minute, guys. Yeah, sorry, guys. So here the what you this is a finally, yeah. So somehow based on what we have done so far, the x, this txb, right? So this is nothing but txb. txb is which is equal to x square. So the whole thing should be equal to x square. Okay. Now based on that, we put C11 we try to find out C11 equal to x square over like this one. Yeah. The thing is, the problem is this has to be C11 has to be purely a function of C11 was supposed to be a constant only. Okay, so here what we are getting is a function of x. Yeah. So unless we have this x itself as x square, meaning that if x is equal to x square, then only this will be the constant, otherwise it will not be constant. Yeah. And it's possible to find out this equal to this is equal to x square. Basically, this is not the right way of doing it. If you put it there, like if you put it here, this will be like this. Yeah. So then what we get finally, in any case, what you are getting is like you multiply here and you finally get of this form, right? But the thing is, if you put this value and in the original equation, what you may not get equal to 0. Yeah. This only indicates one thing, that the t is not really we call variables are not separated. Variables are not really separated. Basically, that's the conclusion. Because if you try that way, if you put that values here, and if you are not getting equal to 0, that means whatever we did the calculation, that is not valid. We have to think something else. And what something else? Well, this is the problem what Fourier himself worked on. Okay, this is the problem which led to Fourier series. Okay, so we started with a Fourier law which says that Q is equal to minus k gradient of t. So this is what the Fourier law is. And heat conduction is basically this is involved. When you are working on 2D problem or 3D problem, then you will encounter the same scenario that we have got. Then what to do? Now, thing is, although variables are not separated basically, but we get some ideas from here. And what is the idea? Ideas are like this. Now, what we have is, in general, if you look at, we added right here only, we're saying that there may be a lot of possibilities. So this is the possibilities, right? We can write like that, yeah? And we know that any function can be like written as a Fourier series, yeah? And even this one can give you Fourier series, x square you can give you. It gives you x square. But only thing is, once you have determined the beta, finally this has to also appear here, right? This appears here. So we also have to put beta here somewhere. Yeah. So that means we have to take care of that. We did not do yesterday. Okay. So what we will do, we will we have various components. So let's say our x is given by, let us say, an. We write instead of gamma, we'll write an sine n pi is the one solution, right, for various n's, and corresponding y is also given as the coefficient, some coefficient, let's say called bn sine h, and here instead of b we write n pi over a. So that's what that is, right? So that will be consistent then, and then the solution will be, we propose a solution like this. So far what we get our x, one of the solution is x is equal to an sine, right? Then you have n pi over a, which is beta, right? This is nothing but beta x. This is the solution. And y is equal to bn sine hyperbolic and n pi over a y. Both of them are solutions. Only thing is we will multiply first. So basically t xy is becomes an bn sine n pi over ax sine h n pi y over a. So this is the, because both of them should have the same beta, so that's why this is the beta, right? So since beta, we just write it here, where beta is equal to n pi over a. Yeah, so we write like that. So this is a beta. So both of them are connected by same beta. So that's why we have. Okay, so that means simply that t xy, we can also write it as cn. Same thing we are writing cn. This together becomes cn, and then sine n pi over a, sine n pi over ax, and sine hyperbolic n pi x over a. Yeah, where cn is equal to an times bn. Okay. General purpose. Still if you want to find out t x b has to be x square. Can this achieve the same x square? Possible? It's not possible. So that means if you put cn sine n pi over a x and sine h n pi b over a, this is sinusoidal here, x square. It's not possible to do it. Yeah, so it's not possible this way. So we have to take a general form of txy will be a summation n equal to 0 to infinity, and then you have a cn sine n pi over a x and sine h n pi, sorry, this should be y, n pi y over a. This is the general solution. Now it's possible to get x square. Okay, so that means from the general solution, t x y or b is equal to summation n equal to 0 to infinity cn, right? Then sine n pi over a x sine hyperbolic n pi over ay so instead of y, we had b here, which is equal to n equal to 0 to infinity Cn sine hyperbolic n pi b over a. So this is a constant, this also becomes constant, right? And then you have sine n pi over ax, right? So let's call this thing as d. So basically we have n equal to 0 to infinity dn sine n pi ax is equal to x square. Now, is it possible to do it? Now it's possible to do it, because any function you can write it as a Fourier series, and you can do now this one, you can do it now with this. Yeah, it's possible to do it. Okay, so now how will we can now use this one, and we can find out dn now. How do you find out dn? Possible now. Just write possible now, and we have to apply this condition to find out the values of dn. So if you, let us say we have I equal to 0 to n dn sine, right, n pi over a x. We integrate 0 to a, the x, so 0 to a, for dx will be equal to, because both are equal, right? We have to make both equal. So we multiplied by, we have this, sorry, we have this, don't write this one yet, and this, and then sine n pi over ax, same thing, yeah, dx. So what we did, the original function, this one, multiplied by sine n pi a over x will be equal to 0 to a x square sine n pi x dx, right? So what we did is multiply sine, this one, multiply this on both the sides, extra, right? So sine n pi over ax, this we multiply both the sides and integrate. So that's what we did. So we have, this is the one we multiplied both the side, and then dx, and then integrate 0 to a. We did that both the sides. And since you know that this sine, this one is orthogonal, meaning that you must have studied already the Fourier series, and you can do yourself. You can expand it. You multiply by this one, you will find out that the only the integration of that, when this and n here, when they match, that only will give you non-zero value. Otherwise, all other value will be zero only. So meaning that, or you can try yourself, you will get in this case dn. Okay, so dn multiplied by a over 2 will be equal to this 0 to a x square sine n pi ax dx, or simply you will get dn is equal to 2 over a, 0 to a, x square sine n pi a x dx. So this will give you all the coefficients, basically. So your solution is txy is equal to summation of yeah. Okay, now, okay, so before that, we also have to find out one thing. So Cn, what is Cn equal? So if Dn is like this, Cn becomes, so we also had Cn earlier, right? So we said our this here, yeah, this is Cn, right? Cn, this is general form. So this, we have to find out Cn first. And Cn is nothing but Cn multiplied by this is Dn. So Cn will be Dn divided by this, right? Sine h n pi b over a. So we find out Cn is equal to Dn divided by, right, sine hyperbolic n pi b over a, right? So general form Txy, which was a summation n equal to 0 to infinity, we had Cn, so we can write, we can still write Dn. We write Cn only, sorry, Cn, and then we have sine n pi x over a sine n pi sine hyperbolic n pi y over a. So this is the solution now, where Cn is given by this, where Dn is given by this. So this is the solution, how you do it. Yeah. So basically what we see here, since this is summed together, the x form, the x, the function, y function, both are multiplied and also summed, basically. So actually this is not really separated, variables are not separated, but still the method gives you that at the end. Yeah. So yesterday we thought it is purely separated, but this not worked out, and hence we got the anomaly. Okay. So this is this problem is something that I think this is a historical problem, and Fourier himself, actually, while working on that, discovered this Fourier series. So it's a really very important, as you know. Yeah. So any question, guys? Okay, so let me save it first. Okay, so we will now start let's start a new whiteboard. Okay, now we will now what we have done so far is we looked at the we derived the equation, and the equation was the gradient, the divergence of the gradient of temperature plus Sx, where this is the source term, that is equal to 0. Yeah, that's what we did now, right? Okay, now next thing is basically you see that the whole thing is scalar one. Finally, this comes to a scalar, right? So this is the scalar value, and this is vector, but vector dot product, so makes it a scalar. So total a scalar, only one equation. Yeah. Now we have to. This is what is the also you call it the strong form. Now we have to solve it. Analytically, we know how to solve it now. Just we saw an example. Separation of variable is the best method. You can do it. Or we use the finite element analysis to solve it numerically. Yeah. Now look at the analytical solution. Analytical solution as such for very simple geometry. Also, it was kind of complex solution, right? And now consider you have geometry which is complex. Then material may be non-linear. All kind of things will come into picture, and then how to solve it analytically, it becomes very difficult. And hence you have the finite element method that is going to solve it. Yeah. Okay, now given this, which is you call it a strong form, now we have to convert into a weak formulation. Yeah, similar to what we have done in case of 1D problems. And hence, what do? You multiply by W. So you have del dot del T, right, plus Sx, yeah, and dx. Okay, only thing here is W is a function of xy now, and let's write here itself. Okay, maybe right here. W is a function of xy, and here we cannot write x, right?
Sir?
Yeah.
Sir, force will also be a function of x and y.
Yeah. Yes, you're right. So this also will be x and y. True. Yes. So this sources will be also x and y. So we write accordingly x, y like this. Yeah. And here we are writing here omega, meaning that omega is the domain, right? So this is a domain. Yeah. Okay. So now this you have W, X, Y, and then this is the domain. For the whole domain, we are going to integrate it, right? Yeah, and that will be equal to 0. Yes. Now, how to do this further? You have now you can expand, so you can write or, right? And then you have for the whole domain, you have W, which is for a function of Wxy, and then you have del dot del T plus d omega plus omega W xy s xy d omega is equal to 0. So you have two terms, number one term, number two term, and let's see how it works out. Okay. Now, next one is, let's take the first one now, right? First one is equal to integrator over the whole domain. Okay. Where when we say domain, that this is the domain, right? This is the omega, where this is 2D, but it may have irregular surface. Yeah. So this omega. Okay. this is donation, how you denote it, like omega for the domain, and the boundary you use the gamma. Okay, like this. Okay, now this you write w. So I'm not writing as a function xy, just we write w only, and then we have this dot del t, right, and d omega, like that. Okay, now we have to convert this into something. Yeah, why? Because this one gives you right now is equivalent of double differentiation, and we have to convert that into a single differentiation. So how to do it? Yeah, so for that we have to work on this. We have to find out what is how we can do it. Yeah, okay, now we have to expand, basically, right? We have to expand it. And how are we going to expand? Now, there are two things involved here. One is what we call is the divergence theorem. Okay, so first let's two things are involved. One we'll call which is known as divergence theorem, and second is what is known as, that we will find out later on. So first in divergence theorem. Okay, and what is this? This one is, this is relevant to what we're talking about, right? So this you should be knowing from your mathematics courses already. And it says that if you have a function, maybe it may be the like divergence of anything. So let's say this is divergence of a function, theta is a function, let us say, right? Like this one, and defined over the whole omega. This is given by this is the integral over the whole domain, but this can be converted into integration over the boundary only. So that's why this integration over the boundary, this is the boundary, right? This boundary is gamma. And also this is the closed integration, loop integration. That means you have to start and you have to finish it like this. Yeah, okay, and then you have theta. You can just write theta here, and then you have a dot. We write dot here, and you have del. Instead of that, you write n here, and instead of this, you are going to write d gamma. Okay, this comes from mathematics. And what is the meaning of this is that if you want to find out a gradient of, if you have to integrate a gradient of a function, then you just need to just integrate this theta dot n over this boundary only, where n is this is the n. So n unit vector perpendicular to the boundary, okay, and projected outward. Okay, so unit vector which is on the boundary, which is perpendicular to the boundary, but this is projected outside. Yeah, so this unit vector multiplied with this function itself at the boundary. What is the value of at the boundary, and then you integrate, you will do it, right? Okay, so this is divergence theorem that we have to make use of. Okay, it has different form actually. So if you have gradient, also you can apply the same thing. So if you have omega, then gradient of a function theta and d omega will be equal to closed loop integral over the boundary, and then you write theta here as, then you have this, you can write n, and then instead of d omega you write d gamma, and you integrate, okay, over the boundary, and you will get the value. Okay, so this is a area integral, and this is the line integral. This is the difference. Yeah, so you are integrating over the loop basically like this. Yeah, any question, guys? This comes from mathematics, so this you must be knowing already. Okay, okay. Now, based on this, we will go further, but before that, let's also, we have to take one more step, and this one, if you have to find out how to do it. So let us, we have to integrate this by integration by parts. So we will use this divergence theorem, but before that, let's expand this one. Okay, so basically how to get this one. Yeah, so if we have del dot w, yeah, del dot w okay, so just to have one example, like if we apply the divergence theorem, let us say we are applying divergence theorem of this on this del dot w del t. Yeah, so then where we have this del here, we have del here, and then we have theta, the whole thing is theta, right? Whole thing is theta, so we have theta, and then if we have 0 to, sorry, not 0, but omega, d omega will be equal to, okay, this is the closed loop integral over the boundary, and then you have, we will have this one, so you write w del t, right? And then what do you have? You have dot, you will have dot, so whole thing dot n, and you will have d gamma. So we are from here, right? So let's call it 1. This is the divergence theorem. So from 1, right? Let's say you call it 2. This is just another example. You can have. So from 1, you get this. This is an example of that. So somehow we want to get this somewhere, so we can convert it. We have to put that in this form. So what I mean to say is, we have right now like this. Yeah, and in order to apply like do integration by parts, yeah, we will this we have to convert into the form in which that gives us the usual form that we are used to for solving, right? So this is just one example, and this is the one we will also get it. Okay, so now we will look at the like integration of parts. Like in order to do this by in order to integrate this one, we have to convert this into a few other form, and then we will use the divergence theorem to convert. We will get this term while we expand this term. We do when we do integration by parts, we will get this form, and this form we will convert into this form using a divergence theorem. So that's what we did, all kind of thing. Okay, so now let's go to the actual thing, and then we can come back here and we can apply that. So we did already here, so that when we are deriving we don't get stuck, so we derive the whole thing now. So now we will go back to I, right? So we have I is equal 1 is equal to infinity, then we have no, not infinity but omega, then you have W, then you have del dot del T, yeah. So okay, guys, you should also have K term somewhere. Okay, so we did not put K, so K will be here like this. Okay. But K is a scalar anyway, so K can be out, no problem, but still we have to write those here also. Let's put K here. Yeah, okay. K here. Okay, so we have so far this. Okay, okay. Now let us see now. So we have this dot W K yeah, which is will be equal to what, where K is constant, so we K equal to constant, yeah. So this is equal to, we'll have K times this dot W del T, yeah. Okay, which is equal to K, and then we can have here this is nothing but del over del X I plus del over del Y J dot, and we have W, which is a function of X, Y both. Then we have del T over del X. Yeah. Okay. What we can do here, instead of writing that way, we will this whole thing we can write at Q, so that we are not confused. So put K here. Yeah. Okay. So that becomes del equal to minus. We can write it is a minus, then W, then Q. Right? We write like that. we have converted back to q now, so that we have minus here like this. The minus because as you know that q equal to since we have a q equal to minus k del t, and hence we are writing this way, so we converted back to this form, so that is easy basically here to understand also and operate. So we have put minus here because of this. Okay, so we'll not write this way. Okay, so is equal to minus, and then we have, okay, no need to cut like this, we'll just cut this. Okay, so we put minus here, and then we have this, then we have w, yeah, and then we have q. So q is nothing but qxi plus qyj, right, like this. Okay, is equal to minus, and then if we see here, this is a double, what we'll get is del over del x times wqx plus del over del y times wqy. Okay, so this is elegant. That's what that's why we converted it back to this. Is equal to minus, and then we get qx dw over dx plus, yeah, plus q so dw over del w over del x times qx plus w del qx over del x plus del w over del y qy plus w del qy over del y. Yeah, we just expanded that. Okay, and which is equal to you see here, we now this one and this one, this term together, this term and this term together. Okay, so we get minus, and we have w and w q del qx over del x, del qx over del x plus del qy over del y plus we get this one now, right? So we have del w over del x, so del w over del x multiplied by qx plus del w over del y qy, the whole thing, right? So this is the same thing but rearranged, and which is equal to minus, what is this one? There we have w, and then what is this? This is nothing but the divergence of q, simply, right? This is divergence of q. Yeah, divergence w times divergence of q. Then you have this value, and what do you get here? You get plus, and this is nothing but, if you see, this is a gradient of w, so you have gradient of w and dot q. That's what you have, right? Yeah. Okay. So now we can convert back to Q is equal to minus K gradient of T, right? If you put it back, then this becomes equal to W, right? This dot becomes K, this, okay, no need of this one. Again, you put the minus here, and then it becomes plus dot, and you have K gradient of T. So you get gradient of W dot gradient of T term. So that means what? This we started from this value, right? So we started from this W right. We had started from that. So this equal to, so this is equal to this. Okay, so that means, and we have this one. No, sir, just a minute, guys. No, that is not the same thing. Just a minute. This is W here. Okay, so not this. We had started from here. Okay, so W was inside. Okay, so we started with this form where W was inside, and we derived that one. So we have W here. That's why we have here, and hence in the equation, if you see here, we have W outside, and then we have gradient of K multiplied by the divergence of K times gradient of T, right? So this value, we have to expand this one. So in order to find this one, this value is nothing but what we got here, this one, right? So this is, so that really means that W gradient of K, the divergence of K gradient of T is equal to this dot W K gradient of T minus this one. Yeah, so minus K, minus this value. So we will write it as gradient of W dot K gradient of T. Yeah, so we will put this value now in the original equation. Yeah, so this the I, so we have I is equal to infinity, the omega, and then we have this. Yeah, so del dot W K gradient of T W dot WK gradient of T d omega minus minus the second term, which is this one, gradient of W dot K gradient of T d omega. Yeah, and we already worked out this one. Through we have applied this one, we worked out already. So let us see, we converted that into a line integral already. So this one, so if you have K here, so let's call it 3. Yeah, so if you have this dot this, then we applied the divergence theorem to change from here to here, right? From here to here. So we will use the same thing, apply the divergence theorem. So is equal to the first term, divergence theorem, that becomes W K gradient of T, right? Gradient of T, and then we have dot N, line integral. Yeah, so we applied the divergence theorem, minus you have, we write here, minus omega gradient of W dot K gradient of T d omega. Yeah, so from here to here, divergence theorem. Okay, guys, that is all for today. We will continue further on Monday. Okay, thank you. Any question you can ask?